Hello, and welcome to your first pre-calculus flipped lesson. Today we're going to look at section 1.1, which deals with the rectangular coordinates. The rectangular coordinate system, which is also referred to as the Cartesian plane, represents ordered pairs of real numbers by points in a plane. Now we form our rectangular coordinate system by taking two number lines that intersect at right angles, and these two number lines are the x and y axis. The point where the x and y axis intersect is called our origin. And if you recall from Algebra 1, the two axes will divide a plane into four quadrants. Quadrants 1, 2, 3, and 4. And then each point that goes on our rectangular coordinate system is called an ordered pair, and they're referenced by a set of parentheses with x usually being listed first, followed by y. So this right here is an example of your x-axis, which is your horizontal axis. Your y-axis is the vertical axis. And we start out with the quadrant 1 right here, and then we go counterclockwise for quadrant 2, quadrant 3, and quadrant 4. Our point of intersection, as we mentioned, is called the origin. So for our first example, it says to plot the points 1, negative 2, 4, negative 3, 5, 0, and negative 3, negative 1. Now, if you notice, this horizontal line right here is our x-axis, and this vertical line right here is our y-axis. This point of intersection is our origin, or the point 0, 0. So from there we're going to plot our points. 1, negative 2 means I'm going to go 1 in the horizontal direction, in the positive direction, and negative 2 means I'm going to go down 2 units. So I have a point, 1, negative 2 right here. Then I'm going to go 4 in the positive direction for x, so 1, 2, 3, 4, and then down 3. For 5, 0, I'm going to go 5 to the right, which is right here, and 0 in the vertical direction, so that would be right here. And negative 3, negative 1 means I'm going to go 3 units to the left and 1 unit down. So these are my points. The one nice thing about a rectangular coordinate system is that it allows you to see relationships between your x and y variables. So let's go ahead and look at example 2, and we'll see how that relationship can be shown. Example 2 says from 1990 through 2003, the amount A, which is going to be represented in millions of dollars, spent on skiing equipment in the U.S. are shown in the table, and T is going to represent the year. We want to sketch a scatter plot of the data. From the table, as we mentioned, this column right here is our year T. Our amount, A, which was in millions of dollars, is given right here, and we have to represent that data on this coordinate plane right here. Now, the one thing I notice when I look at my years is I start at 1990 and I go in consecutive years all the way up through 2013. So what I'm going to do, instead of writing 1990, 1991, 1992, and so on, I'm going to say that when T equals 0 is going to represent 1990. That way, when I look at my number line here, the horizontal direction, I know that my origin right here is going to be 0, and that's going to be 1990. Then the next one will be 1991, or 2 is going to be 1992, 93, 1994 is going to be represented by 4, and so on. So then I'll just continue this pattern, and I don't have to write as much this way. Now, for your vertical axis, I notice that my data ranges somewhere between 400 and about 725. So what I'm going to do is I'm going to go in and I'm going to draw like a little squiggle line to represent a break, and I'm going to start my data at 400 here. Then I'm going to go in increments of 25. So the next one will be 425, 450, 475, 500, 525, 550, 575, 600, 625, 650, 675, 700, and the last one will be 725. Now the one thing that is extremely important when you guys are plotting data is that you actually label your X and Y axis. If you do not label it, I don't know what increments you're using, and I won't be able to help you out with any partial credit. So please be sure to label your axis. So now all I have to do, now that I have everything identified, is go in and plot my points. So I see at the year 1990, which we said was going to be 0, I have 475, which is right here. Then for 1991, I have 577, which is going to be just over the 575 mark. 1992 is 521, so that's 2, and then just over 500, not quite to 525. 1993 is 569, which is going to be just over the 550. 1994 is just over 600. 1995 is just over the 550 mark. 1996, we're going to jump up to just over 700. 1997 is closer to the 725 mark. 1998 is 718. 1999 is 648, so we're going to be just under the 650. 1990, let's see, that was 1999, so 2000, which is now going to be represented by 10, is at 495, or just shy of 500. 2001 is 476. 2002 is 527. And 2003 is 464. So when we look at this set of data, we notice that from the year 1990 to the year around 1998, we kind of have an upward slope or an increase. And then all of a sudden, it's kind of like when we hit 1999 and forward or onward, it looks like we have a slight decrease here and then a big drop here. So this is how rectangular coordinate system graphs can actually help us see like maybe trends or things that are going on. Another thing that the rectangular coordinate system allows us to do is it allows us to calculate distances between our points. Now, the one nice thing with a rectangular coordinate system is that everything is based on right angles. So because of that, we can use the Pythagorean Theorem. And if you recall from geometry and algebra 1, the Pythagorean Theorem says for a right triangle with a hypotenuse of length c and side lengths a and b, then we have a squared plus b squared will equal the square of our hypotenuse, or c squared. Now if you recall, the converse is also true. If a squared plus b squared equals c squared, then we know that we have that right triangle. The Pythagorean theorem will really help us when we're looking to find the distance between 2 points, because in order to find the distance between these 2 points, we're really going to use the Pythagorean Theorem and know that this side length here and this side length here are going to be like our side length of A and B, which we notice does form a right angle. So I know that A squared plus B squared is going to equal C squared. So here, my A squared length, we'll say, is x squared, or I'm sorry, x2 minus x sub 1, and our B length is going to be the difference between the y values, or y2 minus y1. So if I take these two, square them, and then add them together, that's going to give me length D. And again, this brings us to our distance formula. And the distance formula says that D is equal to the square root of x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. This leads us to example 3 that says to find the distance between the point -5, 7 and 3, -4. Well, we were just given this distance formula that said that we have x2, the square root of x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. Now if you want, you can label, and it doesn't matter which one you call point 1 or point 2. So I'm just going to call this x1, and this y1, and this here will be x2, and this here is y2. So if I go ahead and plug in my points, I now see that I have x2, which is 3. So we'll say the distance is equal to the square root of 3 minus my x1 value, which is a -5. I'm going to square that quantity, and then I'm going to add that to y2, which is a -4, minus y1, which is 7, and I'm going to square that. Please make sure you show your work so that I can give you partial credit. So now when we simplify, 3 minus a -5, this is really going to become a plus. So I really have 8 squared plus -4 minus 7 is going to give us a -11, and we're going to square that. So I end up with the square root of 8 squared, which is 64, plus a -11 squared. Now really that's a -11 times a -11, which will give us a positive 121. And if I add 64 and 121, I end up with the square root of 185. So we can either leave it like that, or we can simplify it and see that we get something around 13.6 units. Now example 4 says to show that the points 4, 0, 2, 1, and -1, -5 are vertices of a right triangle. Now you can plot these, and we will at the end, but you cannot assume that just because it looks like a right triangle that it is a right triangle. You actually have to prove this. So what I'm going to do, just for organization, is I'm going to call this point 1, this point 2, and this point 3. So what we have to do is we have to, in order to prove that this is a right triangle, we have to prove that we can go a squared plus b squared equals c squared. So we have to find the distances between the points 1 and 2, 1 and 3, and 2 and 3, and see if there's that Pythagorean relationship. So what I'm going to do is I'm going to go D, and I'm going to go 1, 2. So that tells me I'm looking at the distance between the points 1 and 2. And I'm going to take and use the Pythagorean Theorem. So x1, y1 are going to be from point 1. x2, y2 are going to be from point 2. And I see that I have 2 minus 4, the quantity squared, plus 1 minus 0, the quantity squared. So this is going to give me the square root of 2 minus 4, which is a negative 2. And I'm going to square that and add it to 1 minus 0, which is going to give me 1 squared. Negative 2 squared is 4, plus 1 squared is 5, so I end up with the square root of 5. Next, I'm going to look at the distance between my point 1 and 3. So I'll just keep 1 as my x1, y1, and 3 as my x2, y2. So that means I have negative 1 minus 4, the quantity squared, plus negative 5 minus 0, the quantity squared. Negative 1 minus 4 is going to give me a negative 5. So I have negative 5, that quantity is squared, plus negative 5 minus 0 is still a negative 5, and that's being squared. So this is going to give me the square root. Negative 5 squared is 25, plus another negative 5 is squared is going to give me 25, or this will give me the square root of 50. And the last point that I have to find the distances between are between 2 and 3. So to go ahead and do that, I have the distance between 2 and 3, and I'm just going to call the point 2 my x2, y2 and my point 3 x1, y1. So this gives us the square root of 2 minus a negative 1 becomes 2 plus 1, the quantity squared, plus 1 minus a negative 5, which is really 1 plus 5, the quantity squared. And if I simplify that, so this is going to simplify down to 2 plus 1, which is 3 squared, plus 1 plus 5, that quantity is 6, or 6 squared. So I really end up with the square root of 9 plus 36, and 9 plus 36 is the square root of 45. So if you notice, I have a square root of 5, a square root of 50, and a square root of 45 as my 3 side lengths. So what I need to do now is I need to use the Pythagorean Theorem to prove that these side lengths are actually the same. Well, because the square root of 50, which is right here, is the largest number, this is the only thing that I can have as my hypotenuse. So I'm going to call that my C value. And I'm going to then say that a squared, which is the square root of 5 squared, plus my b squared, which would have to be the other side length, or the square root of 45 squared, should hopefully equal, if this is going to work, the square root of 50 squared. So the square root of 5 squared, if you recall, is 5. The square root of 45 squared is 45. And then the square root of 50 squared is 50. So 5 plus 45 does equal 50. So I then just proved that I have a right triangle. And if you want, you can go ahead and plot these points just to look at it and see. So if we do that, I see that we have 4 in the positive direction, 0. We have 2, 1, and negative 1, negative 5, which is right here. And if you connect these points, you'll see that it doesn't necessarily look like a right triangle, but because we just were able to prove that the Pythagorean theorem could be used, we know that it is a right triangle. Another thing that is important when dealing with rectangular coordinate systems is to calculate a midpoint. Now, if you remember, the midpoint is really finding the average values of two coordinate points. Okay, so the midpoint between the points x1, y1 and x2, y2, if you recall, is x1 plus x2 divided by 2, which is the average of your x coordinate points, and then y1 plus y2 divided by 2, which is the average of your two y coordinate points. So for example 5, we want to find the midpoints of the lines joining -6, 1 and 7, 4. So I'm just going to call this x1, y1, and x2, y2. So I'm going to take the average of my x points. So we'll say midpoint is equal to -6 plus 7 divided by 2. And the average of my y values are 1 plus 4 divided by 2. So -6 plus 7 is going to give me 1 divided by 2. And 1 plus 4 is 5 divided by 2. So I end up with the midpoint being at the coordinate 1/2 and 5/2. Now with example 6, it says during a football game, the quarterback throws a pass from the 32-yard line 40 yards from the sideline. The pass is caught on the 3-yard line 15 yards from the same sideline. How long was the pass? Now for me, the easiest thing to do would be to kind of sketch out what's going on here. So I'm just going to kind of sketch a football field here. Okay, at least I know it's not exactly to scale. So if we have a football field, and we'll call like this down here the end zone, okay, and this right here will be a sideline. So what I'm going to do then is I'm going to come in here and I'm going to put 0, 0, because everything's going to be based off from this end zone right here and this sideline. So by doing that, when I go through and read my problem again, it says that my quarterback is throwing a pass from the 32-yard line 40 yards from the sideline. So what that tells me then is I am 40 yards off the sideline, which will be over here somewhere, and on the 32-yard line, which is going to be in my vertical direction. So we'll come up here and we'll say if this is your 50-yard line for halfway, then 32 is going to be somewhere down in this region. So this right here has the coordinate point 40, 32. Then the next sentence says the pass is caught on the 3-yard line 15 yards from the same sideline. So 15 yards then off from that sideline is going to be roughly right here. And we said that it was on the 3-yard line. So we're going to be a lot closer to this end zone. So we'll say something like this. And this point now has the coordinates 15, 3. So if I want to know how long the pass was, I now have 2 points that I can calculate the distance from. So we'll say the distance is equal to the square root. And what I'll do is I'll call this the 15, 3 will be my x1, y1. The 40, 32 will be my x2, y2. So I'll end up with 40 minus 15, the quantity squared, plus 32 minus 3, the quantity squared. So 40 minus 15 is going to give me 25 squared, plus 32 minus 3 is going to give me 29, and that's going to be squared. So when I simplify this, I end up with the square root of 1,466, which is approximately 38, and I do have units with this, so it would be 38 yards. So the quarterback threw the ball 38 yards on that pass. Our next example says, in 2003, Company A had an annual revenue of $15 million and $17.2 million in 2005. What is the predicted revenue in 2004? In this case, we know what the revenue was in 2003 and in 2005. So the relationship with 2004 and 2003 and 2005 is that 2004 falls right in between, or it would be the midpoint of 2003 and 2005. So in this case, we don't really have to look at the years or our x values. We can just then look at our y values or the average or midpoint of our annual revenues. So if we do that, I see that we have 15 million plus 17.2 million, and we're going to divide that by 2. So 15 plus 17.2, if we divide that by 2, that's going to give us $16.1 million. So in 2004, we can predict that the revenue was $16.1 million. Now, if you recall from geometry, another thing that we can do with our coordinate points is we can translate them. And if you remember, a translation to the right or upward is a positive translation in the x and y direction, and a translation to the left or downward is a negative translation. So for example 8, we want to take the vertices of a triangle, -1, -3, 5, 1, and 2, 4, and find the new coordinate points of a triangle that has been shifted 2 units to the left and 3 units downward. So what that tells me then, because I'm going 2 units to the left, that's in the negative direction, or to the left, and 3 units downward would be in the negative direction as well. So I have to subtract 2 from my x values and subtract 3 from my y values. So the coordinate point -1, -3 is going to become -1 minus -2 is going to give us a -3, and -3 minus a -3 is going to give us a -6. The coordinate point 5, 1 now will become 5 minus 2 will give us 3, and 1 minus a -3 will give us a -2. And my third coordinate point of 2, 4 is going to become 2 minus 2, which is 0, and 4 minus 4, which is 0. So these right here are the translated coordinate points of that triangle. Now the last thing that we're going to look at in section 1.1 deals with common formulas for area, perimeter, and circumference, and in some cases volume. These formulas can be found on page 7 of your textbook, and these are basic formulas that I do expect you to know. I will not give these to you on a test or quiz because it is expected that you know them by now. And you can go ahead and review these. If you have any questions, please let me know. So our last example for section 1.1 says a beach ball has a volume of 904.32 cubic inches. We want to go ahead and find the radius. Well, a beach ball, if you recall, is a sphere, and the volume of a sphere is equal to 4/3 pi r cubed. So what we have to do now is we have to plug in what we know, which is our volume. So I have 904.32 cubic inches is equal to 4/3 times pi times r cubed. So now I have to isolate this r cubed value so that we can get r by itself in the end. So to do that, we have 904.32 5.32, and we're going to divide everything by this 4/3. Well, dividing by 4/3 is really the same thing as multiplying by 3/4. The next thing I have to do is I have to get rid of this pi, which means I'm going to have to divide everything by pi, and that is going to give me r cubed. Well, if you type this in your calculator, right now I have that r cubed is really equal to something around 215.89. Okay, now I would leave that exact value in your calculator just so we don't have rounding errors. Now, if you remember back from Algebra 2, to get rid of that cube exponent there, we have to take the cube root. So in other words, I'm going to take and raise all of this to the 1/3 power. And when we do that, my calculator gives me 5.9989. So I can pretty much approximate that at 6 inches for the radius. Please, please, please include your units. And now for today's fun fact. Today's fun fact deals with the term X-ray. The X-ray was discovered by Nobel Prize winning physicist Wilhelm Conrad Röntgen and is referred to as the Röntgen ray by those in the field today. Röntgen himself called his discovery the X-ray, borrowing the X from the algebraic symbol for the unknown. His discovery was purely accidental and at the time difficult for him to comprehend. Hence, his reference to the unknown or the X factor. And this fact came from the book I Didn't Know That by Carolyn Evans. Have a great day.